Bismillahirrahmanirrahim. Today we have a second lecture of discrete structures. In first lecture we have studied introduction to the course, propositions, logical equivalences, truth tables, compound propositions, and I have given you some examples of translating English to logical form and some logical form to English. Today lecture outline is, today we will study logical equivalences, De Morgan's law, tautologies and contradictions, and we will study also some laws of logic, and at the end we will study conditional statements or conditional propositions. So let's start logical equivalences. By definition, if we have two propositions, then the propositions are called logically equivalent if and only if they have identical truth values for each possible substitution of propositions for their proposition variables. We denote a logical equivalence of two propositions as you know, P is equivalent to Q, and the sign between P and Q is, this is the sign between P and Q, which is called the equivalence. So if we have the logical equivalence between two propositions or two compound proposition, we will write them as, for example, or before giving some examples, I'll show you how to construct or prove logical equivalence between two propositions or compound propositions. There are two methods by which we can show the logical equivalence between two propositions or compound propositions. The first method is to construct truth tables corresponding to both propositions, and then by watching the truth tables we can prove or we can show that whether the two propositions are equivalent or not. The steps which involve the equivalence, the proving of equivalence relations, equivalence propositions, are construct the truth table for P. And second step is construct the truth table for Q using the same proposition variables, and then check each combination of truth values of the proposition variables to see whether the truth value of P is same as the truth value of Q. If in each row the truth value of P is the same as the truth value of Q, then we say that P and Q are logically equivalent. If in some row the truth value of P and Q are different, then we say that the propositions are not logically equivalent. For example, if we want to prove the logical equivalence between these two compound, this is a compound proposition, and on the right hand side we have a proposition P. If we construct the truth table of these two propositions, here in the truth table P have two possible values, true or false. Not P will have, obviously here we will have F, which is false, and on the second line we have true, which is opposite to the F false of this proposition. And double negation, by taking the negation again of P, we have the possible values of double negation of P, true and false. Now if we compare the two columns here, this and this, we can see clearly that in the first row both truth values are same. Here we have true, and on the second column the first row is also true, and in the second row here we have the truth value of P is F false, and in this column the truth value is also F. We can see that the truth value in each row of these propositions, not P and P, are exactly same. Therefore we can say that these two propositions are logically equivalent. If we take another example, in this example we will show that the two compound propositions are not logically equivalent. For example, if we have this compound proposition not P and Q, and the other compound proposition is not P and not Q, we'll show by using truth table that these two compound propositions are not logically equivalent. Now we construct the truth table for these two propositions. Here we have two propositions P and Q, so the possible values of the truth table are, for P is true true, false false, and for Q we have true false true false. Now to construct not P and Q and not P and not Q, we need not P, not Q, and P and Q. So by step we will construct the truth table for these two compound propositions. First we take the negation of P, for which we will have, for truth value not P we will have false value, and for here again for the truth value of P, if it is true we will have not P is false. Here we have false, here obviously we will have true, here false true, and then not Q, corresponding to T we will have F here. For F we will have T, for T we will have F, and for F we will have T. Now we need P and Q. As we know that P and Q is a compound proposition which has the truth value as a true if and only if both P and Q have truth value as true. So for P and Q, the truth value in the first row will be true, and in all other rows we will have false, as we have seen in previous lecture. Now the negation of P and Q. Now as we know that P and Q is given in this column, and the negation of P and Q, for T we will have F, for F we will have T, for F we will have T, for F we have T here. Now we construct not P and not Q. We have two columns of not P and not Q here, and conjunction between not P and not Q will be true only if both are true. Here we can see that we have in the last row the both values are true. So here we will have true, and in all other columns we will have false value. Now we have constructed the truth table for both compound propositions given in the question. For this value, we can see that we have these two columns corresponding to the given two compound propositions which we are required to prove equivalent. We can see that in first row we have same truth values, but in second and third row the truth values are not identical. Therefore, the two propositions or two compound propositions given here are not logically equivalent. So we have proved in this example that the two compound propositions are not logically equivalent. Now this was the first method to prove logical equivalence of two compound propositions. The other method, we use some rules of logic to prove logical equivalence between two compound propositions, which we will study later. Now, De Morgan's laws. What De Morgan's law state? The negation of and proposition is logically equivalent to the or proposition in which each component is negated. And the other De Morgan's law states that the negation of an or proposition is logically equivalent to the and proposition in which each component is negated. Logically, we express the De Morgan's laws as: the first De Morgan law is for the conjunction. For example, if we take the negation of conjunction of two propositions where P and Q are two propositions, then the first De Morgan law states that negation of P and Q is logically equivalent to negation of P or negation of Q. And the second law of De Morgan is about the disjunction. If we take the negation of the disjunction of two propositions P and Q, then this will be logically equivalent to negation of P and negation of Q. In these two laws, we can notice that the negation operator, when operates on the conjunction of two propositions here, it converts the conjunction into disjunction, and the two propositions are being negated. This is the first law of De Morgan. Similarly, as in the second law of De Morgan, if we operate the negation on the disjunction of two propositions here, this sign is obviously, as we have studied in previous lecture, is of disjunction. Then this disjunction will be converted into conjunction, and the two proposition will be negated separately. So this is the De Morgan's law, which we will use frequently in the logic or in proving equivalence of two compound propositions. For example, here, how can we negate the following compound proposition by using De Morgan's laws? The first question or example is that John is 6 feet tall and he weighs at least 200 pounds. Here we can see that we have two propositions. The first proposition is John is 6 feet tall, and there is a sign of conjunction and here, and the second proposition can be he weighs at least 200 pounds. Now if we write it in the logical form, how shall we write it? If we suppose P is the proposition, which is, if we write the P is the proposition that John is 6 feet tall, and the other proposition we suppose Q, he weighs at least 200 pounds. Then how can we write it in the logical form P and Q? Now the negation of P and Q will be what? By using De Morgan's law, this must be equivalent to not P or not Q. So how we will write the negation of this statement by using De Morgan's law? The solution is John is not 6 feet tall, and here we have disjunction he weighs less than 200 pounds. Now we can see that the first proposition is negated here, as we have not, and then disjunction converts into conjunction converts into disjunction or here, and the second proposition is also negated, he weighs less than 200 pounds. Here we had he weighs at least 200 pounds. At least means he weighs more than 200 or 200 plus, and the negation of this will be less than 200 pounds. Another example here, the second example, the bus was late or Tom's watch was slow. Now here we have disjunction operator, and we have two proposition. For example, this is P and this is Q. Then by using De Morgan's law, we can write the negation of this statement as, first we will write the negation of the bus was late. What will be the negation of the bus was late? The bus was not late, or we can say that the bus was on time. The or will be converted to and the second statement, the negation of second statement will be Tom's watch was not slow. So we can write here the bus was not late and Tom's watch was not slow. So this is the negation of this statement by using De Morgan's law. Next, I take an example from mathematics which involves the inequality. How we will apply De Morgan's law on inequalities. For example, if we take this inequality minus 1 less than x less than or equal to 4, you have seen frequently such type of relations or expressions in mathematics. So what does it mean in mathematics? We can write this statement or this expression as minus 1 less than x and x is less than or equal to 4. So in De Morgan's law, how we will negate this expression? We know that the negation of x greater than or equal to minus 1 less than x will be minus 1 greater than or equal to x, because as we know that in mathematics we have the negation of greater than is less than or equal to, and the negation of less than is greater than or equal to. Similarly, the negation of greater than or equal to will be less than, and the negation of less than or equal to will be greater than. So here we write the negation of minus 1 is less than x as minus 1 is greater than or equal to x, and the operator and the conjunction operator and will be converted to the disjunction operator or, and the negation of x less than or equal to 4 will be x greater than 4. So the negation of this expression will be this. So we can apply De Morgan's law to negate such type of expressions in mathematics also. Next, we'll study the tautologies and contradictions. Now, what is a tautology? By definition, a tautology is a proposition form that is always true. A compound proposition can also be a tautology, or a simple proposition can also be a tautology. Now, what is the condition for a compound proposition to be a tautology? Is that its truth value is always true, regardless of the truth values of the individual propositions. And a proposition whose form is a tautology is called tautological proposition. Similarly, on the opposite, the contradiction by definition is a proposition or a compound proposition is said to be a contradiction if its every possible truth value is false, or you can say that a proposition is said to be contradiction if it is false in each value in each row of its truth table. A proposition whose form is a contradiction is called a contradictory proposition. We take some examples of tautologies and contradiction. For example, in this example we will show this expression or this compound proposition is a tautology, and the second expression, this, is a contradiction. We will show that these two propositions are tautology and contradiction using truth table. So to construct the truth table of these two compound propositions, we need only one proposition, P. All possible truth values of P are true and false as given in the first column of the table, and negation of P will be, F will be written here corresponding to T and T corresponding to F. Now we can write the negation, the truth values of the compound proposition P or not P. As we know that disjunction operator is truth value is true if at least one of the proposition is true. Here we have true and here we have false, therefore here we will have true. In the second row we have F, false and true, here we will have true. We can see that each possible truth value of this compound proposition is true, regardless of the values of the truth values of the individual propositions. What does it mean? It means the compound proposition has all the truth values as true, and we don't care about the individual truth values of P and not P. We can see that there are false values in the truth table of P and not P here in these columns. P is true and false, not P is false and true. But in the compound proposition here, P or not P, every possible truth value is true. Therefore, this compound proposition is a tautology. And at the last column, P and not P, we can see that we have every truth value of this compound false. Therefore, this compound proposition is a contradiction. We can see also that the individual proposition has truth values as true and false both, but this compound proposition has false value in all rows, in every row. Therefore, this compound proposition is a contradiction. Now, if we say that if T is a tautology and C is a contradiction, then we can easily show that P disjunction T is equivalent to P, and P conjunction C is equivalent to C. Here T is a tautology means this proposition T will have all true values in its truth table, and contradiction C, this will have all false values in its truth table. So we can easily prove that P or T is equivalent to P and P and C is equivalent to C. I left these two equivalences as an exercise to prove yourself. Now we'll study some of the laws of logic. The first law of logic is commutative law. Commutative law states that we can interchange the position of propositions. Here, if we have P and Q, this will be equivalent to Q and P. So, by interchanging the position of the individual proposition doesn't affect the compound proposition. So, this is called the commutative law. This law holds also for disjunction, that is P or Q is equivalent to Q or P. We can prove these two equivalences using truth tables easily. The next law is associative law. This law states that if we have P and Q and R both are in brackets here, you can see, and this compound proposition is logically equivalent to P and Q and R. Here we can see that associative law states that we can interchange the brackets here. If we have P and Q and R, then we can write P and Q and R. So this law is called associative law for conjunction. This law also holds for disjunctions. For example, here we have P or Q or R. This is logically equivalent to P or Q or R. So here we also notice that we can interchange the brackets here. So this compound proposition is equivalent to this compound proposition. The next two laws are called the distributive laws, which states that in the first law we can see that here we have this conjunction, and inside the bracket we have disjunction here. This law states that P and Q or R is logically equivalent to P and Q or P and R. So here we can notice that P and Q or R. How we shall remember this law, distributive law? How we write the logical equivalence of this compound proposition using distributive law? First we write P, and P has, here we can see that P, we write P and the first proposition, and then P and we can say first proposition, and here the first proposition of the bracket, and on the second step we write P and R here, P and R. So we put these two compound proposition in brackets, and between these two compound proposition we write this operator OR. So this is how we can remember or we write the distributive laws. Similarly, we can write the second distributive law, which is P or Q and R. This is logically equivalent to how we write P or Q and R. This will be logically equivalent to, as I told you, we write P or Q and P or R. Here we write P or Q and P or R. This operator will come between these two compound propositions here, and then we write the middle operator here between these two compound propositions. So this is how we can remember, we can memorize these distributive laws. The next law is identity laws, which states that if we have a proposition P and a tautology T, this is always logically equivalent to P, because as we know that T is a tautology, its every truth value will be true. Therefore, the conjunction of P and T, P and tautology, will always depend on the truth value of P, because if P is true, then T is always true, as we know that. If P is true, then this conjunction is true. If P is false, tautology, as we know that it is always true. So if P is false, then this conjunction is false. So this expression or this compound proposition give us the same truth values as P. Therefore, P and T, where T is a tautology, is logically equivalent to P. The second law states that if we have a proposition or a contradiction, then this compound proposition or the disjunction of P and C is logically equivalent to P, because we know that C has all possible truth values as false. For example, if we let's construct a truth table for this compound proposition. We have P, its truth values are true and false. Here we have C, we know that its truth values are always false. Now P or C, what is this? Now P or C is a disjunction between P and C, and we know that the disjunction between two propositions is true when at least one of these two propositions is true. Here we can see that P is true, C is false, therefore P or C is true, and P is false and C is false, and we conclude that this is false. So P and C, we can see that P or C, the truth value is 3 in the first row. Here also we have truth value T. In the second row, P or C has truth value as a false, and P has a truth value as a false. We can see that these two propositions P and P or C has identical truth values, therefore these two propositions are logically equivalent. So we can say that here P or C is logically equivalent to P, or we can say that P or C has same truth values as P. Similarly, we can prove this equivalence, in which T is a tautology. T will have always true values here. The next law is the negation law. The negation law states that P or not P is always tautology. As we can see obviously that if P is true, not P is false, and if P is false, not P is true, and there is a disjunction between P and not P. Therefore the truth values, all possible truth values of P or not P will always be true, and therefore it is a tautology. Similarly, the other negation law states that P and not P is always contradiction. We can also prove this equivalence using truth table, but it is obvious here if P has true value as true, not P is false, and if P is false, then not P is true. So at least one of these two proposition has false value in each row, therefore this compound proposition will always be a false. Therefore we can say that P and not P is logically equivalent to C. So these two laws are negation laws. The next law is double negation law. So if we take the negation of a proposition, we get the same proposition. So it is obvious also, we can prove it by using truth table. We know that the truth value of P in the first row is true. If we take its negation, it will become false, and if we take again its negation, it will again come true. So in each row, in both rows, P is logically equivalent to negation of P. So this is called double negation law. The next law is idempotent laws. These laws are very obvious. We can immediately see that P and P is logically equivalent to P, and the second law is P or P is logically equivalent to P. So in both laws, the truth values of P in each row remains same. Therefore, we can say that P and P is logically equivalent to P, and P or P is logically equivalent to P. The next law is a universal bound law. In this law, the first law is P or T is logically equivalent to T, and the second law is P and C is logically equivalent to C. So here we had identity laws. Here we have P and T is logically equal to P. Here we have reverse of this. If we have P or T, this compound proposition is logically equivalent to T, because we have here disjunction operator, and we know that whatever the value of P, T is a tautology and it is always true, and we have disjunction operator, and we know that disjunction of two proposition is true when at least one of the truth value of proposition is true. So T is always tautology, therefore we have at least one truth value is a true, therefore P or T becomes a tautology. This compound proposition will always be true. Similarly, P and C. Now we have here the conjunction operator. The conjunction operator, or the conjunction of two proposition, is true when both proposition are true. As we have C here, which is a contradiction, which is always false, therefore this compound proposition P and C is always false, which is logically equivalent to a contradiction. The next law is absorption law. Absorption law states that this is basically the special case of distribution law. The first law is P and P or Q is logically equivalent to P. We can prove this logical equivalence using truth table, that for example, I told you that this law is a special case of distributive law. How? In distributive law, we know that we have P and Q or R, and this is logically equivalent to, in distributive law, P and Q, P and R, this, and if two of these individual propositions, any two, P, Q, R, here we have three propositions, P, Q and R. If in these three propositions, if we have any two are same, then we can have absorption laws. So in distribution law, if Q or R, one of these is equal to P, then this left hand side is logically equivalent to the proposition which comes two times in this distributive law. So this is called the absorption law, which is a special case of, you can say, distributive law. Similarly, the second law here is also a special case of distributive law. We can prove it if we have P or P and Q. This is logically equivalent to P. So if we have two same propositions here in distributive law, then this left hand side or this compound proposition will be equivalent to the proposition which comes two times on the left hand side. The next law is negation of T and C. We can obviously say that negation of a tautology is always a contradiction, and the negation of contradiction is a tautology. Now we prove the logical equivalence of this expression or these two propositions, we'll prove this compound proposition is logically equivalent to P using the rules of logic. As I have told you that there are two methods to prove the logical equivalence of compound propositions. The first we have studied by using truth tables. We can prove the two compound propositions are equivalent or not. The second method is to use rules of logic to prove whether two compound propositions are logically equivalent or not. For example, if we take the left hand side here, this is the left hand side of the above equivalence here. Now we can say that we can apply the negation here. If we apply the negation here, then by using De Morgan's law, as we have conjunction here, so we can apply De Morgan law here. So if we apply negation on this, we can obtain negation of P, and will be converted to or, as we stated in De Morgan's laws, and here Q will be converted to not Q. So here we can see that we can apply the double negation law, which states that negation of P is equivalent to P. So here we apply the double negation law, and negation of P becomes simple P. Here we have same or not Q, we have and P or Q. Now we can see that here we can apply distributive law, as we know that distributive law is P or not Q and Q. This will be equivalent to P or not Q, P or Q, and here we will have and. So this statement is logically equivalent to this statement by using distributive laws, as we can see that here this is the same statement as given here. So here we can apply the distributive law to obtain P or not Q and Q. Now you can see that here not Q and Q, we have studied a law here which states that the negation law here, P and not P is always or is equivalent to contradiction. So we can apply this law here, not Q and Q. What is this? This is equivalent to a contradiction. So what is this law? This is basically the negation law, and we can say that Q and not Q or not Q and Q. Here we have commutative law, as we have stated in commutative law that we can interchange the individual propositions, and then applying the negation law here, Q and not Q, it gives us a contradiction C. And then by identity law we can say that, or we can write P or C is always P. So therefore we have proved that this expression on the left in this exercise is logically equivalent to P by using rules or laws of logic. So we can prove the logical equivalence of two compound propositions by using two methods. The first method is the truth tables, and the second method is the laws of logic. Today we shall stop until here, and the lecture summary is this. We have studied today the logical equivalence and how we can prove two compound propositions are logically equivalent or not. We have studied two methods to prove logical equivalence of compound propositions. The first is by using truth tables, and the second using laws of logic. Next, we have studied the tautologies and contradictions, and I have given some examples of tautologies and contradictions to you. We have studied also the laws of logic, and by using laws of logic we have proved in some examples the logical equivalence of two compound propositions. And in the next lecture we shall study the conditional and biconditional statements, their interpretation, and some examples. Okay, Allah Hafiz.